Good evening, sir. Hello.
Good evening, sir. How are you?
Fine, sir.
Okay.
So
Yeah.
we'll start within a few minutes. Okay.
Yeah, no problem.
So good evening, all participants. So today we're going to start the session 9 in the 6 days long FDP on deep learning for computer vision. So today we have with us expert speaker Rishabh Bakul Burua. So he's taking the session on deep learning for computer and robot vision applications. So Rishabh Bakul Borua is a robotics and AI scientist. Currently, he is affiliated to Monash University, Australia. He has received PhD fellowships from universities across 5 different countries like USA, UK, Ireland, Australia, and Malaysia. He completed his master's from Jadavpur University, Kolkata in 2018 with first class second rank. He has filed 22 US, Europe, and India patents, out of which 14 have been granted so far. He has published his research in many reputed journals and conferences. He has been invited to many premier Indian and foreign institutes for talk such as IITs, IIMs, NITs, New York universities, etc. He receives numerous prestigious grants and awards from various organizations. His team at Tata Consultancy Services Research received the Best Research Team Award in the year 2020. His work has also been included in a course at the University of Florida, USA. So, sir will take the session now. Please, sir, you can start the session now.
Yeah. Thank you, Professor Gautam Pal, sir,
Welcome, sir.
for the introduction. Nice introduction. And also, I would like to thank for the invitation to deliver a talk on deep learning and computer vision in this AICTE ATAL FDP program. And also would like to thank Tripura Institute of Technology for inviting me today. So without much delay, let's start because we are on a schedule. So just let me try to share my screen first. I think my screen is visible.
Yes, yes. Sir, you start from the yes.
Yeah. So
Yes, now is okay.
yeah. Okay. So yeah. So this talk is about trends in computer and robot vision. So in my talk, I have put some topics regarding image enhancement for robotics applications. Then after that, 3D vision for robotics and virtual reality applications, and finally some action recognition applications. But according to the time, I will try to cover everything. If not, then I will skip some things as per the time frame that we have. That is 1.5 hours. So let's see how much we can take it forward. So first, before going into the first thing, I'm showing here something, to set the tone of what exactly I want to speak about. So here you can see two rows of images. So first row is LDR, second row is HDR. So LDR means low dynamic range and HDR means high dynamic range. So when we normally take images or videos using our cameras in general, the low-cost cameras. So we take the input in the form of LDR, low dynamic range, where the intensity levels of the pixels are limited to only 2 to the power 8 levels per pixel. So that's why the amount of brightness and darkness in the image is less. I mean, the ratio between the darkest and the brightest region in the image is very less. The ratio is very less. Hence, sometimes we are not able to see the overexposed and underexposed areas of the image, which exactly is happening in the first row. In the second row, it is converted into high dynamic range image, where you can see the first row images are looking more clearer after converting to high dynamic range, because the intensity levels, the brightest and the darkest pixels range is much higher than LDR. So in LDR, we represent each pixel by a bit depth of 2 to the power 8, that is 256 intensity levels. And in HDR, it can be more than 2 to the power 8. It is 2 to the power 10 or 2 to the power 12 or even more. So we have a higher, set of intensity levels to represent the image. So in the first work or the discussions, I will be talking about how we can actually convert this low dynamic range images to high dynamic range using deep learning. And this is a very important problem to be solved in the computer vision perspective, because of deep applications in robot or robotics. So here in the left hand side image, you can see here in the left hand side image, I have put a block diagram. So the first part of the block diagram, that is in yellow, this is the typical camera pipeline, where we click image, and according to the brightness of the scene, whether it is in daylight or inside a room, the brightness of the scene is determined. And finally, we take the exposure time from the shutter of the camera, and we get the high dynamic range image, HDR image. So, but while clicking the image, it is in high dynamic range, but after it gets saved in the memory, it becomes low dynamic range, because typically the screens that we have to display images are not supportive of high dynamic range images. They are only supportive of low dynamic range images. There are special screens designed for high dynamic range images nowadays. For example, your Apple iPhones and Apple laptops, these have inbuilt high dynamic range image or video display technology. So the second part of the image here, the diagram, the pink part is the steps that we take while converting HDR to LDR in a heuristic basis. No, there is no deep learning involved here. So dynamic range clipping, quantization, and nonlinear mapping. These three things happen, and we convert HDR to LDR. After that, so our main task here is to reverse this pipeline. The pipeline that we have here in the image, in the middle part of the image, the pipeline that we are having, which have dynamic range clipping, quantization, and nonlinear mapping. So our job is to create a deep learning model which can actually reverse this process. So we need to do the nonlinear mapping, then quantization, then dynamic range clipping. We need to reverse all these things to get the HDR from the LDR. So in the deep learning part, we will input LDR image and we'll get the HDR image, provided the model is trained to do so and trained to replicate the reverse of the camera pipeline. Okay, so that is the goal of our discussion today, the first part of the discussion. So let's go to the index, what we are going to talk about. So our recent works in this domain, we have explored 4 different things. First is if histograms or histogram equalized images have any impact on HDR content creation or HDR image or video generation. And then is there a gap in the data set or data domain for HDR image generation for deep learning? And then how can we, if there is no sufficient data for supervised learning, how can we create unsupervised or unpaired or self-supervised methods for this purpose? And finally, can we bring physics-based properties into this generation process? Okay. So now coming to the first part, here you can see I am showing a architecture, and it has two encoders. Typically, these two encoders are ResNet 50 based encoder, which depends on CNN type architectures. If you have worked with CNNs and ResNets, you will be able to know this thing. So we take the normal LDR input ground truth through one of the encoders, and we take another input that is created from the first input, that is equalized using histogram equalization technique. So in histogram equalization, generally we create a system where the intensity levels are distributed equally among all the 255 intensity bins in an LDR image. Okay, so this is generally we say we call this as intensity stretching, or contrast or intensity stretching, where we actually distribute the intensity levels into more uniform way, rather than the intensity levels being present in the original image. So here we have these two inputs. One is the original LDR and one is the histogram equalized LDR. We pass it through two ResNet based encoders, ResNet 50. We fuse these two inputs, concatenate these two inputs, and we pass it through a self-attention block of a transformer. So transformer is a very complicated architecture, but in this particular method, we only use a small part of the transformer, that is the self-attention part, that has a query, key, and value, Q, K, and V. We represent the query, key, and value using Q, K, and V. So if someone of you or any of the researchers present in the talk work with transformers or self-attention, then you will be knowing about this thing. After passing it through the self-attention, we pass it through a simple CNN-based decoder having a couple of convolution layers, and we get the HDR output. Sorry. Then there is a loss that we calculate between this generated output and the ground truth HDR output, and we back propagate it through the network to make the network learn this thing. So this is the first thing that I wanted to discuss, that we recently did and published. So after doing this work, we came to know that definitely if we use a modified input rather than only passing the normal LDR input, like equalization of histograms or gamma correction or any kind of pre-processing of the input, if you do, and if you stretch the intensity levels more uniformly across the 255 0 to 255 intensity bins that are present in LDR image, then we get better results compared to other existing methods. So so here we use multiple loss functions, but I will not go into the details of all the losses because most of them are already present in the literature. The only loss that we proposed here is loss number 6, and one more is the loss number 12. So this loss number 6 is a modified version of PSNR that we call as peak signal to noise ratio, that finds the difference between two images and tries to give a quality score of comparison. So we use this as a loss function in our method, but not exactly this PSNR, but a modified PSNR that we call as Weber's equation. So this we used in this method, and this 12, equation number 12 in the screen you can see. So this is another equation that actually finds the difference between the color intensities between two pixels, the input and the ground truth input image and the generated output image. So we calculate the difference between the intensity levels of the color of the pixels, the colors of the pixels. So these two are the novel loss functions that we use. Other than these, the others already are present in different literatures that we have directly adopted. So doing so, we found that our methods results are more clear, and the amount of fidelity of the reconstruction of the objects in the images are very clear. So here you can see we have compared our method, which we call ours in this image, and ground truth HDR is the last column, and the first column is the LDR inputs to the method, and the middle 4 columns are existing state-of-the-art methods. So if you can see clearly, you can see that the last row and the second last rows are most similar to each other compared to the other 4 methods. This actually shows that our method can reconstruct HDR images that is much more closer to the ground truth for that particular LDR image compared to the other state-of-the-art methods. In the left-hand side image, you can see, just I am showing some examples of how histogram equalization works. So the green color graphs are the original intensity levels for the image, and the orange color graphs are the histogram equalized intensity levels of the image. So you can see that how histogram equalization actually stretches the intensity levels into almost equal values for all the intensity levels. So this indeed works well for our method, and this actually proves that if you use the original input combined with some pre-processed correction techniques like histogram equalization or gamma correction, etc., then the output of the deep learning model significantly improves. So here are some quantitative results which shows that our method is better than the existing state-of-the-art compared in 3 different matrices like PSNR, SSIM, and HDR VDP2. So PSNR is very common matrix. Most of us we know. SSIM is structural similarity metric between 2 images, and HDR VDP is a metric that is specifically used for comparing the radiance values of each pixel in a HDR image, not in LDR. So this last one, HDR VDP, is not used in normal LDR images. It is only used for comparing to high dynamic range images. Now coming to the second part, so we also wanted to investigate that is there any gap in the data domain for LDR to HDR translation problem, specifically for deep learning purposes. And we found that there is a significant amount of gap in the data domain itself. So before explaining the thing, I will go and show you this slide where you can see the first row here. The first row comprises of existing data sets. So these different color dots are different data sets present, and we have plotted this in a 2D graph using this UMAP based feature reduction technique, where we reduce the features of the data set into 2 dimensions and projected it. So you can see in the first row there are this red color, yellow color, and blue color dots which represent existing data sets that we have in this domain for LDR to HDR translation problem to train the deep learning models. And in the lower row of images, you can see this green color is the data set that we proposed, which I am going to talk in a few minutes. So this proposed data set is actually trying to fill some of the gaps in the feature space which were left unattended by the previous data sets. Okay. So now coming to the data set. So we tried to do a very interesting thing. So since these games nowadays have high dynamic range and low dynamic range setups for their graphics, So we selected this GTA 5 game. I think most of you might have heard about this game. This is quite a popular game. So we took this game. We tried to use some off-the-shelf tools to capture game playing data from this game directly in both LDR and HDR mode. So this GTA luckily has both LDR and HDR mode of graphics representation. Okay, so we collected LDR HDR pairs from this game, and we created a huge data set which comprised of more than 40,000 LDR HDR image pairs. Okay, for different scenes. So this is the pipeline which we used for data collection. So we used a off-the-shelf tool called Script Hook version 5 plugin. So through this, we captured game playing sequence of 15-20 hours. Then we did data sampling. We collected around 54,000 and 72,000 pairs of LDR HDR images. Then we did a frame similarity check and discarded those frames which are very similar to one another, so that we can create a diverse data set and not a very biased data set. Then we also did some manual cleaning for unwanted scenes from the game. And finally, we had a 40K pairs of LDR HDR images. So this is the table of comparison for all the datasets that we have in this domain and our dataset. So you can see that our dataset has in the wild scenes, then scene diversity and image diversity, which is missing in most of the other existing datasets. And the size is also quite good. It is 40K images, almost greater than all the other datasets, excluding only one, that is city scene. And the resolution is also 512 x 512, which is quite fine for deep learning applications. So in the right-hand side, you can see I have shown some images for different locations, different weather condition, different time of the day, and different objects, which we included in our dataset, so that the scene diversity and image diversity is high in our dataset. In the lower part of the image, you can see we also tried to generate different contrast levels here in the lower part of the image, and different exposure levels, and combine contrast and exposure levels. Okay, so this also indirectly added to the image diversity part of the dataset. So having only one contrast level or one exposure level may make the dataset more biased towards that particular contrast or exposure. So making this multi-contrast and multi-exposure, we tried to mitigate that biasness in the dataset. We did some experimentations, and we found that our dataset performs well, and compared to other existing real and synthetic datasets, which we represent in this table by R and S, our dataset when the models, some of the existing deep learning models for HDR reconstruction are trained on our dataset, the results are better compared to other datasets. Okay, and finally, when we combine other existing datasets along with our dataset, that gives the best results. That is shown in the last part of the table, the last subsection of the table. So yeah, this thing I already talked about in the beginning to show that how our dataset is actually filling the gap in the feature space, which is left void by existing datasets. So finally, we also check how different exposure and contrast levels can enhance the intensity levels across the intensity bins. So the first green color graph is that is the representation of the data set when we have only single exposure levels. The second one, blue color graph, is for multiple exposures. And finally, the last one is for multiple exposures and multiple contrast levels in our data set. So you can see that the last one is the best compared to the other two in diversifying the intensity levels across the different intensity bins, 0 to 255. So these are some of the results which shows how our HDR image, generated HDR image from our dataset is compared with the ground truth, and also the one of the base HDR image from a existing state-of-the-art model. So we also did a KL divergence test, and we saw that the images generated using our dataset trained on a deep learning model are much more close to the ground truth in terms of KL divergence. That is one of the ways to see between two different distributions of data. So typically we use KL divergence to find the similarity between two distributions. So in this case, we represented these images as data distribution by taking into account the RGB intensity levels separately, and we checked, and we found that the KL divergence value for images generated using our dataset trained using deep learning model is much lesser compared to other existing state-of-the-art methods along with the ground truth. Okay, so we also tested our method and our dataset for downstream applications like human body part segmentation and semantic segmentation and 3D reconstruction, 3D human reconstruction. And we saw that the images generated using our dataset can actually add value to the downstream applications by making the downstream applications more accurate in terms of their working. So here you can see in the first image that if we give a normal overexposed or underexposed image, and if we give the HDR image generated using our trained dataset, then the output human segmentations are more accurate in this case. Similar to the semantic segmentation, you can see the output is very fine and accurate in the HDR generation case. And finally, for the 3D human reconstruction, the last one, the bottom image, right-hand side. So you can see that the humans, the orientation and the positioning of the 3D humans in the scene is more accurate in terms of our HDR generated image compared to the other overexposed and underexposed LDR images. So this actually proves the efficacy of the method and our new data set that we have created, that this data set can actually improve the existing state-of-the-art methods learning capability for HDR reconstruction. Now we will jump to one interesting thing. After I talked about the supervised method, and then I talked about the gap in the data domain. Now we'll see if we can do anything in the self-supervised domain. Okay, so this is a very interesting thing that we tried. So normally we have worked in GANs, generative adversarial networks, or different versions of GANs. So in this method, we try to use a cycle GAN kind of architecture. So normally cycle GANs are used for image-to-image translation tasks. Okay, so if we have let's say we have a painting and we want to convert the painting to a real-life image, and then again we want to convert the real-life image to a painting. So we can use a cycle GAN to do that. So we can convert this painting to real-life image, and we can convert it back to painting. So if we consider the painting as X and the image as Y, so from X to Y and from Y to X, both way translation is possible using cycle GAN. That's why it is called cycle GAN. So we can go in a cycle from one type of input to other type of output, then from that output to again the input. So in this method, we tried this cycle GAN along with some other contributions to actually produce a self-supervised kind of method for this particular problem of HDR reconstruction. And one important thing to note in cycle GAN is that you don't need paired data sets. So suppose we want to convert image from X to Y, so you do not need single pairs of X1, X2, X3 with Y1, Y2, Y3. Okay, so you just need to have a set of X and a set of Y, and you can use it for training the model. You don't need a one-to-one mapping between X and Y. That is typically needed for supervised methods, normal supervised methods. So in this method, we tried. So the last one in the table is our method that we call a cycle HDR, and the rest of the methods we compare and we see that our method tackles different problems existing in the state of the art. Like we have tackled the problem of unpaired or one-to-one pairing of datasets in this method. Then we use a heuristic-based post-processing for refining the output, that is HF. Then we use semantic similarity between the images as an input using some off-the-shelf models. We also use contextual information using the same model. And finally, we use using all these methods actually ensures that there is no artifact in the generated image. So normally when we use GANs or cycle GANs or any kind of GAN, there is a possibility of generating images with artifacts, okay, like blur or noise or something. So to reduce that, we have used different methods along with the cycle GAN architecture. And finally, our method can do the both-way translation, that is from LDR to HDR and from HDR to LDR. So this is the overall architecture. So we have two set of generators, GY and GX, and we have two set of discriminators, DY and DX. So typical GAN architecture has a generator and a discriminator. The generator generates images or videos, and the discriminator tries to catch the generator by labeling it as fake. So the discriminator is actually inputted with the real image and the generated image and allowed to identify that the image is real or fake. So when we train this GANs, there is actually min-max game between the generator and discriminator. The generator tries to fool the discriminator by generating images as good as the real ones, and the discriminator tries to catch the generator to actually say that the generated image is fake and not real. So this thing happens in the training process of a generator and a discriminator in a GAN. The same thing happens for a cycle GAN, but in this case, in the cycle GAN case, we will be having two generators and two discriminators. The rest all is similar. The losses will work either way. And there is another loss that is not there in the GAN, that is the cycle loss, which actually is between the input and the final output after the entire cycle is completed. So here we represent LDR with X and HDR with Y. So we give this LDR X as input, we get the HDR Y. Then we put the HDR Y as input to the next generator, and we get the original LDR X. Here we call X cap because it is the generated one. So Y and X with caps are the generated ones, and original ground truth X and Y's are without the caps. Okay. So pretty much clear from this image what is happening. So in the first cycle, from X to X cap, we find the loss between this X and X cap. This is called the cycle loss. Again, for the second cycle, which is between the Y and Y cap, we find the loss between Y and Y cap. That is again the cycle loss. So the forward cycle loss and the backward cycle loss, both losses are there. Okay. So we also use this encoder E here. This encoder is nothing but a clip-based encoder. Some of you might already know that contrastive, language image pre-training we call clip. So this is a kind of an encoder that encodes image and language together. So when there is a similarity between a text and an image, then this encoder puts these two in the same feature space. So similar text and images are put in the similar spaces, and different text and images are put in different spaces using the clip encoder. But in this case, we don't have any text information or text input. We are using two different images, and we pass this via the clip encoder to put it in a similar space. So in this case, we use this clip to pass the generated Y, that is the HDR, and another clip to get the ground truth X, and we concatenate them and we put it to the generator GY as a feedback mechanism. So this essentially gives us the difference between X and Y cap. What is the semantic difference between X and Y cap, and tries to mitigate the difference between X and Y cap using this clip-based encoder. The combined feature representation of this both the E's that is passed to the generator GY. Same thing happens for the next cycle, but for Y and X cap this time. So previously we did it for X and Y cap. Now we are doing it for Y and X cap. Now this generator GY and GX is a special kind of unit that we designed for this purpose. So original unit is it seems like this that I have shown in the image, but here I have introduced the feedback mechanism that you can see in red color, and this feedback mechanism actually has the red color blocks inside its loop. It runs for 4 iterations in each training cycle, and it refines the output of the the decoding blocks that are colored red in this case. So this actually helps in mitigating artifacts in the final output. And finally, we use a heuristic-based post-processing that you can see in the right-hand side, algorithm 1, where we use some specific thresholds to get the underexposed, overexposed, and artifact infected areas of the output, and then we pass it back to the network using a loss function to let the network know that this particular pixels in the image needs to be improved because this contains your underexposed, overexposed, or artifact infected area. These are exposed to artifacts or underexposure or overexposure pixels. So these are the representation of the different losses that we use. So heuristic-based loss, as I explained, we get the different areas, artifact under and overexposure areas, and we create a loss function to find the number of pixels infected using an equation, and we pass it back to the network to make the network learn about these infected areas. Then we have a segmentation-based loss where we actually create the segmentation map of the input and the generated output and try to mitigate the difference between the segmentation classes between both the input and the output. And we call it the LSAM here, and we pass it back to the network to make the network know that if a generated image is semantically similar to the input image or not. Okay. Then the cycle loss I already explained, and the contrastive loss is a new loss that we have designed here, where we try to, this works similar to the clip concept, where we find the semantic similarity between images using cosine similarity function. Okay, so we have a batch of images that we pass to the network as input, and we in this batch, for example, let's say the batch contains 4 images as shown in this image here, the top right image. So the first image from this batch X will be will find the cosine similarity with all the generated Y's of that batch, and as it should be similar only to the first Y, so the first Y and the first X will come closer in the feature space, and the first X and all the other Y's will go in separate places in the feature space. So the red color arrows are dissimilar, and the green color arrow represents similar. So this thing happens for all the input images in the batch, and finally we get a semantic similarity map between the input and the output for that particular batch, and this also serves as a loss function for the network. Okay. And then we also, so apart from all these things, we also try to, after getting this heuristic based, post processing, we get these 3 different types of pixels, artifact, over and underexposed pixels. So we create these maps, feature maps from these pixels, pass them through convolution, and finally add these to different parts of the generator to let the generator know that what are the different areas of the feature map which it needs to attend to for artifact removal, underexposure minimization, and overexposure minimization. Okay, and this is the table which shows that our method, which is self-supervised in nature, is better compared to other some of the supervised as well, and as well as unsupervised or weakly supervised or semi-supervised methods. Only in the PSNR, our method is second best, and one supervised method called ghost-free is best. So yeah, I'll skip this because these are similar experimentations, nothing much to discuss. And this is the backward cycle comparison, where we convert the HDR to the original LDR input. So we compare with other operators which can convert HDR to LDR and some state-of-the-art methods, and we see that our method can do the job better, and the SSIM and so SSIM and PSNR I already talked about. So LPI-PS, the third metric, is another that actually is finding the difference or similarity between 2 images on the basis of perceptual nature of the image. So this takes into account the human perceptual system, that is the way our eye senses the environment, the way the human eyes sees the environment in front of us, around us. So the same concept is mathematically used in this LPI-PS metric. So if we have a high score in LPI-PS, that means that the image is perceptually very pleasing to the human eye, and the level of understandability of minute details of the image is very high. Okay, so SSIM and LPI-PS matrices are better in our case, but PSNR is again kind of second best. So yeah, so this is the scenario. Here you can see some of the images where we have actually removed the artifacts. So our method, the third column, sorry, and the last one is the ground truth. The second one is the existing state of the art, one of the method which produces artifacts. As you can see, there are some artifacts in the wall for the first image. Similarly, artifacts in the sky for the second and the third rows, which are removed completely for our generated image. So these are some other results of our method compared to other methods, where you can see some artifacts in the lamp in the room in the first set of images that is removed in our method. In the second image, artifacts generated in the sky part, clouds part, which is removed in our method. Okay, so yeah, so I would like to mention that while training GANs or cycle GANs, there is a very typical problem that arises, that is called mode collapse, where actually the discriminator actually is fails to understand whether the image is fake or real, and the generator gets biased on one particular type of images. So in that case, the generation quality or the generation fidelity decreases for GANs. So one should be very careful about this particular problem that happens in normally in generative methods. It also happens in VAs. If you have heard about VA, variational autoencoders. So we need to be very careful that the system or the model doesn't go into the mode collapse problem. Okay. So yeah, now going to the last part of this topic, that is how we can incorporate physics-based modeling in this particular problem. So normally when light falls into objects, so we have two types of objects based on physical properties of light. Okay, so first is Lambertian and second is specular. Specular are those objects from which light is reflected in one direction after the light is incident on that object. And Lambertian surfaces are those surfaces where if light falls, it is equally transmitted in equally reflected in all the directions. So for example, here you can see I have shown an image of a particular stone kind of a artifact in the left hand side image. So here the stone part is specular because there are some shiny surfaces in the stone. So light is not distributed evenly across the surface. Some parts light is reflected, some parts light is not reflected in the same way. But the base that is created of stone, rough in nature, you can see that there is no shiny part in the base. On all the parts of the base look similar. So light is reflected in all directions. Okay. So this is a very important property of light when light falls into objects. And this property needs to be taken into account while generating HDR images. Otherwise, the light object interaction, the reflectance, the shadows present in the image can be misrepresented in the generated image. Okay. So here again to show the concept. So when we have high roughness, you will not see any shiny part in the object, and when we have high shininess, you will see some parts of the object is reflecting light the way that is not similar to the other parts, and you will see some shiny parts and some non-shiny parts. For example, the first ball where the roughness is almost 0, we can see the shininess in the object, and when the roughness is 1, we can see that the object there is no reflection from any part of the object in a uneven way. So everywhere the light is reflected in an even nature or even way. In the lower part of the image, you can see the left hand side image. You can see some green color parts, you can see some gray color parts, and these are very prominently represented. And the right color, right part, the albedo map. So albedo is nothing but the base colors or the base hue of the pixels in the image without any interaction of light. So when light falls on image, the color of the object tends to change a bit. Okay, depending on the intensity of the light, the color of the light itself. But when we remove the light component from an object, the basic color of the object comes up, and this basic color is called albedo in light object interaction. So in this method, we try to bring these properties of light object interaction like shininess, roughness, albedo, all these things into account, and try to motivate the model using these properties. So here you can see 3 different images I have shown. So the first image is a overexposed image. The second one created by our current model that I'm going to discuss. And the third one is the second one is a state-of-the-art model, and the third one is our model that I'm going to discuss. So you can see our model's light object interactions in the scene are very precise and clear, while the second one, the middle one, has some overexposed areas in the image which cannot be perceived directly. There are some perception issues in some of the light object interaction areas, like the background wall and some of the lights on the ceiling part and so on. So now coming to our method. So in this method, we actually tried to create on top of a diffusion model. latent diffusion model, where so most of us might be knowing about diffusion models, where we try to create noise and induce noise in the input, and the model tries to predict the induced noise. So the main task of the model is to predict the noise in each timestamp. Okay. So here we use a latent diffusion, where actually the noise is not added to the direct input, but added to the latent version of the input. So we first convert the input to a latent representation using some encoders. Once it is converted to latent representation, we add the noise to that input, and then we pass it through the model for denoising. So here you can see, so the purple part is the diffusion part, and the green part is the part where we actually are taking the raw input images. So this encoders E and E bar are two different encoders which takes different inputs and convert to latent space. We also have the clip, that is the contrastive language image pre-training for maintaining semantics in the generation process, and the D is the decoder that finally decodes the denoised image into the final HDR. We also have DA and VIT on top. You can see DA is the depth encoder and VIT is the illumination encoder. So we take this LDR input, we pass it through DA and VIT and get depth map and illumination map. So this depth and illumination map combined, we pass it through the clip, and then we finally pass it into the diffusion process. So this illumination and depth maps actually tries to give us the precision in the light object interaction. So whenever light interacts with objects, so the depth also is an important factor. So if the object is nearer to the light source, and if the object is far from the light source, on top or on the basis of that, the light will reflects differently, or the color of the light incident on the surface of the object will be different. So we need to take care of the depth perception, the illumination perception of the image, and then we need to do the diffusion process. So now, after getting this depth and illumination, passing it through clip, we also take the input LDR through the encoder E bar, and we also encode the HDR image through encoder E. So first we add noise into the latent representation of encoder E, and then we add the latent representation of the LDR along with the latent representation of the HDR, as you can see in the image. Then we pass this noise added and concatenated latent representation into the HDR diffusion process, where it actually tries to predict the added Gaussian noise. So we add the Gaussian noise first, and this HDR diffusion, which is based on UNet architecture that I already explained in the previous work. Similar kind of a UNet architecture is used for this case as well. And this UNet architecture tries to predict the added noise in each time step of the diffusion process. And finally, after the predicted noise is performed, we pass this predicted noise and the output to the decoder to get the final HDR input. So the story is not ending here. So we also decompose the ground truth HDR into material maps converted into albedo map, roughness map, and metallic map, as I discussed in this previous slides. So objects, light behaves separately for separate objects. So these three different maps, albedo map, roughness map, and metallic map, are the map of the base color of the objects in the scene, the map of the rough objects in the scene, and the map of the Lambertian objects, and the map of the specular objects in the scene. So we separate out these objects so that we can reconstruct their light properties separately without any mix and match between these properties. Okay, so we created these three different maps from the HDR ground truth and the HDR generated, and we created a loss function that mitigates the difference between these material maps, and we pass it through the model to let the model know or train the model on basis of the difference between these material maps, so that the model can better represent the light and object properties while the reconstruction happens. Okay. In the lower part, you can see two equations. The first equation is the equation for the diffusion process, where essentially we first add noise from the Gaussian distribution or normal distribution that is represented using n, 0, and I, and we use t number of time steps for representing for adding each noise. Okay, for each iteration of the training process. Then this epsilon is the ground truth noise that is added into the latent representation, and epsilon theta is the noise predicted by our diffusion process. So theta is the model parameters. So epsilon theta is nothing but the HDR diffusion that I have represented in the diagram, unit based. So our goal is to minimize the noise, that is the difference between E epsilon minus epsilon minus epsilon theta. That is the main goal of our model. So this epsilon theta, we condition this epsilon theta with encoder E, as already explained. Then T is the time step of adding noise. Then epsilon and then E bar that represents the latent representation of LDR, and EH represents the HDR latent representation. And finally, LEMB, that is the combination of the depth information and the illumination information passes through the clip. So final output of the clip is the LEMB. That is the last term of the equation. Okay. So this is we use a L2 loss for calculating this. The second one is nothing but a L1 loss between the three material maps that I explained. So in this, we can see that our method again performs well in terms of most of the matrices for this two data sets that we use, CT-SYN and HDR synthetic and HDR real. In the second table, you can see we tried to do a zero-shot testing by using a separate data set that was not used for training, completely separate data set, and we see that our method generalizes well on in the wild data set. All the matrices were better compared to other state-of-the-art methods. So these are some of the visual results compared to other state-of-the-art methods, and you can see how our method fares compared to other methods. Our methods images are most close to the HDR generated, the ground truth HDR, the last column, compared to the other state-of-the-art methods. Okay, so with this, so this particular problem of HDR generation, I will conclude at this point, and I will go to the next part where I am talking about two separate additional things which are hot topic in current computer vision or robot vision research. The first one is the digital humans. So creating 3D humans for virtual reality applications or human robot interaction applications. And the second one is action recognition in dark. So normally we have seen a lot of work been already done in the field of action recognition from videos and images, but there is very less amount of work being done in recognizing actions from videos which are taken in dark scenarios, either in nighttime or low lit regions. Okay, so both of these are very important from robotics perspective, because robots day by day their usability and applicability are growing in our day-to-day lives, and robots might need to even work in dark regions sometimes. So they need this kind of capability of recognizing objects and actions in dark. So now coming to the first thing. So the first thing, I will not directly talk about digital human generation using videos, but a special case where we are actually trying to study the problem of sign language generation for deaf people. So this has some societal impact. So we have taken up this project in Monash University in collaboration with some other members, where we try to reconstruct digital humans from videos and images for sign language representation for deaf people to interact with the generated 3D human avatars. Okay, so the motivation behind this is that there are around 396 million people, according to World Health Organization, which are deaf, and those deaf people, they find difficult to communicate with normal people, and also they find ignored or neglected when it comes to communication in terms of university setups or conference setups, or to express what they want to know, to tell you, or something like that. So it is important that we have some computational tools which can actually generate 3D human avatars performing sign language to assist and help out these deaf communities. So this particular work, we focus only on Australian sign languages. So if you are not aware, then I would like to say that different countries have different sign languages. So we do not have a standardized version of sign language like we have for natural language. For example, English is a standardized language which normally is spoken across the globe, and most of the people know, and it is the common language for communication in abroad, right? But sign language don't have such standards. Okay, we do not have a standard way of communicating in sign language. So each country has its own set of sign languages or set of signs for sign language. So in this case, since we are based at Australia, so we tried to first do the job for Australian Sign Language. So our goal is to take a set of images or continuous scenes from a video where a person is performing sign language, and we want to actually create a 3D model of this sign language performance, or the person along with the sign language. So here you can see a brief idea. A person is trying to deliver something using sign language, trying to say something using a sign language, and in the lower part, this is the output of our method, which actually creates the 3D model. So here it seems like 2D because we are representing it in the screen, but if you use a virtual reality setup, this will actually appear as a 3D model in front of you, like a real human being. Okay, so in this problem, we tried to first create a data set using this gloves, VR gloves and VR setups that is there in Monash University. We have a lab which can actually capture 3D data. So we call different deaf people in our lab, and we told them to perform some signs that we wrote in a piece of paper and gave them, and they performed these signs, and we captured the 3D information by letting them wear the 3D gloves for 3D gloves and 3D suit to gather the 3D information from the body of that deaf person. So after doing that, we found that there are lots of redundant kind of signs which are not consistent with the human movements. So normally there is a biomechanical constraint in human movements, and we incorporated a filter through which we remove those particular movements which are biomechanically not consistent with humans. For example, here you can see the pink color, the hand in the right hand side is not biomechanically consistent with human movement. It doesn't seem feasible. So we tried to create a biomechanical constraint that removes this kind of scenes, this kind of 3D data from the data set, and only keeps the plausible poses. Same for fingers. We checked whether the finger positions captured using the Manos gloves. The gloves that we used are called Manos gloves that captures the accurate 3D positioning of the fingers. So whether this positioning of the fingers are biomechanically consistent or physically plausible or not. If not, then we try to put them into the closest angle which is biomechanically consistent with real human finger movements. So this way we refine the data set first. Then these are some of the biomechanical constraints that we incorporated for different arm movement and finger movements. Okay, so yeah, so now we tried, after doing so, we tried to create two models for body and hand separately. So we tried to use this variational autoencoder, VA, that was trained on our ground truth data. So we tried to create two different priors using this VA. One is for the body, one is for the hand, as I already said. So why we use this prior using VA? Because pose priors for hand and body can significantly actually impact the final output quality of 3D reconstruction. Okay, and plausibility in human poses is an important thing that we need to tackle, because existing models, existing works that create 3D digital humans from 2D images and videos has the problem of plausibility or physically possible pose of hands and body. Since hand movements and finger movements are quite separate than the body movement, so we created two different models here. We didn't want to create one model for the entire body. So after that, this is a typical diagram of the variational autoencoder that we used. We use a simple encoder and a decoder, and we use a latent space in between, and we pass our data set through this encoder decoder via the latent space and created this latent space. Further, this latent space will be used in the final generation pipeline, which will generate the actual 3D human body. This is the overall architecture of our method. I will not go into the details because of time constraint. So the important things to know here is that we give input as a sign language video where a person is performing sign language, and we take the initialization of hands from an existing method called hammer, shown in this diagram here. Then we use another state-of-the-art method to initialize the 2D key points of the human body. Then we use this hand initialization and 2D key points further, along with the priors that we modeled in the previous slide here. We modeled the priors using the variational autoencoders for the hand and body. We combine these inputs with our hand and body prior together, and we have some loss functions here. And finally, we get the 3D human, digital human performing the sign language. Okay, so these are some of the results. You can see that we give this input sequence of images of sign language performance by a particular person here. In the below, you can see one state-of-the-art called Signify, and our method we call Dex Avatar, and another method called EVA. So our method, you can see closely that the fingers of the hand are most closely replicating the real hand movement of the human. In the left hand and the right hand side, you can see there is some issue in the orientation problem of the body and the fingers, and some implausible finger movements as well in the Signify case. But in our case, the middle one, Dex Avatar, you can see the fingers are very accurately reconstructed from the human input image. Another example you can see here. So another sign language performance by a human and the reconstruction quality compared to other two state-of-the-arts, the middle one being ours. So the finger movement, the hand movements are very plausible and physically replicating the actual hand movement of the human. But in the left-hand side and right-hand side cases, there are some implausibility and self, intersection between the hand fingers, which should not happen physically. So these things are actually removed by using our generated data set and training process. These are some other, reconstruction output of different sign language scenes. The input frame being on the top, the state of the arts in the middle, and last one, our output. Same here also, you can see our output quality from the finger generation perspective and the hand orientations are quite, accurate compared to the other state-of-the-art methods. So in the table also, from the quantitative perspective, our method is performing best compared to other state-of-the-art methods. So here lower is better. So this is nothing but the vertex to vertex error between the ground truth position of the key points in 3D and the reconstructed position of the key points in 3D. Key points means the key skeleton points of the human that we use for reconstruction of the entire human body. So here lower means there is less error between the positioning of the 3D key points between the ground truth data and the reconstructed 3D human. So our method performs best compared to other state-of-the-art methods. So now, coming to the last part that I will skim through in the next 10 minutes. So this is a work that we have done again recently with some collaborations with other researchers from our university here at Monash. So how can we solve the problem of action recognition in low lit conditions or dark conditions? So first thing we tried here is we not only tried to give dark input to the model, but also tried to give some enhanced output using Retinex enhancement theory and gamma correction theory. So we also tried histogram equalization at this case, but histogram equalization was not giving good results. Only Retinex enhanced and gamma correction was giving good results. So we, resorted to using only Retinex enhanced frames and gamma corrected frames. So you can see here the difference. The first row, dark frames. The second row and third row, the same dark frames are actually corrected using this Retinex and gamma, where you can see the humans or the person performing the action more clearly compared to the dark frames. Here we use a special type of contrastive learning where actually we try to push the dark frames from the same class into one feature space and dark frames from different classes into separate feature space. And another one where we put bright frames and dark frames of the same class into same feature space and bright frames and dark frames from separate classes in different feature space. So this essentially will help the model to know which actually frame comes from which feature space, and on basis of that the model can decide whether the frame is from which class or which action class, to be precise, because the feature space consists not only of the dark frames but also the bright frames which are of the same class, okay, in the feature space. That's the beauty of using contrastive learning. And in all the contrastive learnings that we have used till now, we use this cosine similarity metric for this representation of similar and dissimilar feature spaces. So this is the overall model that we use, and this model is nothing but a teacher-student based model, where the teacher model is heavy and the student model is light. In the teacher model, we pass the Retinex enhanced frame and the dark frame via two CNNs, and then these feature vectors that we get are then represented using the contrastive learning that I talked about in the previous frame. And then we use a dynamic feature fusion module that fuses the feature vectors from both these input input branches, and finally we pass this through BERT. BERT is a kind of advanced kind of RNN, and it has some attention modules similar to transformer. So this is BERT is actually used as a pre-LLM model. So before LLMs were introduced, BERT was used extensively for the same purposes. After passing it through the BERT, we finally pass it through the action classifier module, and then we get the action classes. Now, the action classes that we get from the teacher model is passed to the knowledge distillation process, where we compare it with the action class of the student model. In the student model, we pass actually dark frames from the same class to a CNN, and we do a self-supervised contrastive learning as shown in the previous as shown here. So here are two types of contrastive learning we did. The left hand one is self-supervised, where we have dark frames of same class into one category of feature space, and dark frames of separate classes into different feature space. Supervised one is where we use both bright and dark frames for keeping the feature space either similar or dissimilar. Since we use bright frames in the left hand side, we call it supervised contrastive, and since we use dark frames only in the left hand side, we call it self-supervised. So here we use a self-supervised method in the student model, and then finally the action classifier predicts the class after taking into account the self-supervised loss and the CNN-based feature extractor. And finally, the class predicted by the student and the teacher goes through a distillation process, and there is a distillation-based loss function that tries to minimize the gap between the action class predicted by the teacher and the student. So we created a teacher-student model here to actually minimize the inference complexity. So if you wish, if you wish, you can use the teacher model directly for the prediction, but in that case, the model will take a lot of time for inference, and the resources needed will also be in the higher level. But if you use only the student model after the training is done, then it will take much lesser time complexity, and resources will also be lesser in this case. So we use the teacher only to train the student model. After the student model is trained completely, we remove the teacher model and only use the student model for inference. Okay, where we give dark videos as input, and we get the class of the action being done by the human in the dark video. So this is the description of the dynamic feature fusion module that I described in the teacher model. So we take the inputs, we combine the feature, we pass them through global attention and local attention. We do element-wise addition. Then we do a weighted attention. Then we pass it through the softmax. And finally, we get the features, and we fuse the features. And this fuse feature goes into the BERT, as explained in this architecture. So again, here we can see that we did a good job in predicting dark action from dark videos. So the accuracy is considerably high compared to other state-of-the-art methods. So we take a lot of state-of-the-art methods to compare, and we saw that our method, we call ACT-LUMUS, only the student part to be precise. So we removed the teacher part after doing the knowledge distillation using the action classes of both the teacher and student model. So you can see our methods accuracies are better than most of the, or all the methods in most of the cases. Okay. So yeah, with this, I think I would like to close the presentation, and will be open for questions and answers. If anyone has any questions about anything that I talked about, or anything related to computer vision or robot vision. Thank you. So if anyone has any questions, they can also type in the chat.
Hello participants. If any question, so participant can ask our expert.
Yeah, anything related to today's talk or any other, you can ask any basic questions regarding computer vision or robot vision as well. It need not be directly related to today's talk. I'd be happy to give some inputs for that as well.
So if participant have any question, so they can ask.
Yes, yes, I can hear you. You can also type the question in the chat.
So sir, if participant have no question, so we can conclude the session here.
Yes. So yeah, if anyone wants to talk about any of my works or uh, wants to ask any question, they can directly even contact me via mail also. You can give my mail to the
Okay,
participants
okay,
if anyone is interested to ask anything about any topics related to computer vision or robot vision. So I'd be happy to help them out. No problem.
okay, okay, okay,
Okay then.
okay,
Thank you so
okay,
much.
okay, sir. Okay.
Uh, I'd
Thank you,
like
sir.
I'd like to thank again Professor Gautam Pal for his invitation to deliver a talk in this AICTE ATAL FDP on deep learning and computer vision. Thank you very much.
Thank you,
So,
sir. Thank you.
okay. So, yeah, thank you and all the best for the other sessions remaining in this FDP.
Thank you, sir.
I think one more session is coming up, right?
Yes, yes, yes.
Yeah, yeah, yeah. Okay, okay. Thank you, sir. Thank you so much.
Thank you.
Hope
Thank you.
to visit Tripura Institute in future
Yes,
as
sir.
well.
Sure, sir. Sure.
Yeah.
So our next session will be start within say 5 minutes. So we can take 5 minute break. So after 5 minutes, our next session will start. Thank you. Good evening, madam.
Good evening,
Hello.
sir. Good
Good
evening.
evening. Good evening. So, madam, we'll start our session. So, before that, we introduce you.
Sure, sir.
So, dear participants, so now we have with expert speaker Dr. Jagriti Saini, and madam will take the session. Uh, take a session on computer vision and in disease diagnosis with pre-trained models. And Madam is the founder and owner of a startup company named Eternal Restem, working in the direction of overall student growth and welfare at multiple levels. The core idea of the firm is to provide relevant guidance and training to students on data science, machine learning, IoT concepts, along with adequate research practice, research paper writing skill, integration of digital teaching learning tools, quality education, soft skill, behavioral education, and emotional and social well-being. Jagriti Saini holds a diploma in electronics and communication engineering in the year 2010 from GPW Kandaghat and completed her BTech in electronics and communication engineering in the year 2013 from HPU. She received a master's degree in electronics and communication engineering from NIT Chandigarh, India in the year 2017. She was awarded a gold medal for securing the highest percentile in the entire university during her master's degree. Jagriti completed her PhD from NIT Chandigarh in the year 2022 with affiliation to Punjab University. She received Inspire Fellowship from the Department of Science and Technology, India, for carrying out her research work. She also completed her postgraduate certificate program on data science and business analytics from Purdue University, USA, in collaboration with IBM and Simplern in the year 2023. Her current research interests include data science, artificial intelligence, Internet of Things, etc. And she delivered expert lecture in many organizations across the country and abroad also. So, madam, please start your session now. Thank you,
Thank you
madam.
very much, sir. So, good evening, everyone. I'm sharing my screen with all of you to share with the session of the day. And as you already know, in this particular session, we'll be talking about disease diagnosis using computer vision and some deep learning applications with pre-trained models. And I suppose in previous sessions of this course, you people have already gone through the basics of deep learning, basics of computer vision. In some previous sessions, some other experts have given the theoretical as well as practical knowledge about all these concepts to all of you. So
Madam,
I'll
your screen is not visible. My
is it
slide is
working,
not.
sir?
Hi, yes, now
Right,
it's
I'll be coming to this part. Don't worry, I'll come
okay.
into this part.
Okay.
So uh, in this session, we'll be mainly talking about the practical aspects. So instead of going ahead with PPTs, etc., I'll be going directly with the implementations using Python programming, so that all of you can see the practicality behind any kind of application that you can have using computer vision, etc. So anyone who is equipped with laptop or computer right now, they can execute it with me side by side. Throughout the session, whatever codes I'll be writing here, I'll be doing live coding in front of you, and I'll be sharing codes side by side in the chat box, so that you can implement them side by side, and you can also visualize results on your side. So I think you need not to write them with me. Rather, you just listen to what I'm saying, and I'll be sharing codes with all of you so that you can copy and run them on your side, just to save time and just to spare time for better understanding as well. First of all, let us see what kind of data set we'll be using in this particular session. Since this is about disease diagnosis, so I have taken one simple data set that is publicly available online. It is Kaggle dataset that all of you can easily access. I can share this data source also with all of you, so that later on also, if you want to explore this, you can do that easily. For instance, this one I have shared here. On this data set, first of all, why I'm taking this data set? The main benefit is that this is a small data set. Since all of you may be aware that deep learning models generally take a very long time to run, to execute results. But we have to finish, at least we have to learn the concept within the available time of 1.5 hours. So I was looking forward for a small size data that can be executed easily within the available time. So that is why I picked up this data set, which contains a limited number of images. You can observe here 137 images from COVID-19 and 317 total images for viral pneumonia as well as normal chest x-rays. So basically 3 different categories they have that we would have to predict by utilizing a pre-trained model. And the pre-trained model that I'll be using for implementation will be EfficientNet B0, the basic version of EfficientNet, basically, I'll be using here. And many of you might have already heard about EfficientNet model that works on, actually it is by default trained on ImageNet dataset. But here we'll be using it for our application. And for that little bit of initial training layers, I'll be modifying in EfficientNet B0. And then we'll be improving its level of accuracy based on the available data set in hand. So you can observe here that currently this data set contains 2 different folders. One is test folder, other is train folder, you can observe here. And in the train folder, if I click on this, we have 3 sections. And similarly, in the test folder, we have these 3 sections. In each one of these sections, there are a range of images that are already listed inside. Depending upon what kind of predictions we are doing, accordingly, the data sets are generally arranged. So this is basically a 3-class prediction we'll be doing. And data set is already in the train and test repositories. So the very first thing we need to do is we need to grab this data set from Kaggle and take it to some Python platform. In my case here, I'll be using Google Colab, which is an open source platform that all of us can use easily. And if any of you are using Jupyter Notebook, I suppose all the codes may be same on that platform as well. However, Google Colab is pretty simple to use. If any of you are using it for the first time, then also I can guide you. You just have to go on any of your browsers and then search for Google Colab directly. And it will go to the official website. In case if it is not taking you to the official website, it will at least take you to this platform like this. And you can click on this and it will take you to the home page of Google Colab. I'm just explaining this for those who are doing Google Colab for the first time, but I suppose many of you might have done this already. So in this section, make sure you have logged in using your Gmail account, like I have done here. In your case, if you are using it from your laptop, if your personal computer is there, it will automatically take your login from the browser. But if it is not taking login due to some reason and you are seeing a sign in option here, then just add your Google credentials or your Gmail account and enter into the platform. The benefit of using Gmail account with this is that you will be able to save your code directly in your drive so that you can access it anytime later. You need not to do any additional saving effort in that case. And also the dataset I'll be loading in the drive folder directly. So all of you will be able to easily get it from there as well. That will be an easy process for all of us. So this is the initial step for the sign in. And once you have signed in, the next step is to open a coding sheet on Google Colab. For that, you need to go to the file option on top left corner. Click on this and then click on new notebook in the drive. As soon as you click on this, it will take you to a new window here. That will be basically your coding window now. And that window only will be using for running our entire code further. So the previous one I can close now, and this one is the window that we need. All of you can quickly confirm me in the chat box if you are ready up to this. so that we can proceed further together. I just need to ensure that everyone is going fine on the other side, so that we can learn further. Quickly, you can post in the chat box if you are ready with the platform. If anyone needs any help, they can also let me know. I'm here to assist you. At least those who are willing to do it side by side, please be responsive in the chat box. Then only I'll be able to help you. Otherwise, maybe I'll go fast, or maybe you will be left behind. So that will help me to stay on your pace. So the very first thing we need to do here is, yeah, sure, the Google Colab file I'll share later on. That will not be a problem. But yes, if you do it side by side, there are many things that you will learn, because when we do it practically side by side, then only we realize if we are confused with some point, and then only we'll be able to inquire about it. So that is definitely your choice, whether you want to do it side by side or maybe later. So I'm just renaming this sheet over here. I'll be renaming it with disease diagnosis. So you can give it any name based on the project that you are working with, or maybe with the reference to your FDP. The sheet name you can update. And now the very first thing I'll write here is, I'll use a text cell on Google Colab as well as on Jupyter Notebook. All of you might be aware that we have both coding and text cells. Text cell I'll be using every time to keep some reference points for all of you, so that you can understand which part of the code I'm writing. And the code cell I'll be using to run the actual Python executable codes. So in this section, first of all, I'll write get dataset from Kaggle. So this is the very first task or very first step we are following here. And in order to get this data set, that is your this one that we have already observed, we'll write a simple code. We will import it with the help of Kaggle Hub. And we first need to get the Kaggle Hub ready on our system. The codes I'll be sharing, so don't worry about that. First, try to observe what we are doing. I'm just importing some essential libraries. Kaggle Hub, I need to establish connection with this Kaggle repository from where I'll be getting my dataset. A shuttle library is essential for shell utilities that help us to run several common tasks on the file, such as copying files, moving files, or archiving files or directories, etc. So for that shuttle I'll be using. And OS will need to run across the different paths that we'll get for the dataset while saving it on either on the drive folders or maybe from the main server's datasets. So OS library I'll be needing over there. Now what I'll do here is, first of all, I'll be setting up path for the data. And for that, I'll be writing here Kaggle Hub, that is the main library I'll be using. Inside this, I'll be using dataset download function. And from where I'll be downloading this dataset, that we need to mention from the file address itself. So what I'll be taking here is, I'll take this portion of my Kaggle repository, and I'll place it right here inside. So now Kaggle Hub .dataset download, and inside this I'm passing information about my file path. After this, I can even print the original file path from Kaggle Hub. So it will be printed like this here. So just to observe, this is optional, just to observe, if you want to see the Kaggle Hub path from where we are getting dataset, that will be printed over here. Now, the next thing what we will be doing is, make sure you have logged in with your Gmail account, then only you'll be able to run next part of the code, because I'll be establishing connection with the drive directly now to save our dataset in the drive directly. So in your respective drive, the dataset will be saved accordingly. So what I'll do here, google.colab import drive. First of all, importing my drive into the Google Colab, and then I'll be mounting that drive with a specific address that will be created right here. So I'm putting this information. Observe here that this is the file section of my Google Colab. If I click on this, I'll just wait for a while, and you will observe here some sample data set will appear. This portion is appearing right now. This is the content portion of your Google Drive. I'm inserting one more thing here that will be my drive, my personal Gmail drive that I'll be connecting here. So after I'll run this code, there should be one additional folder that will be my drive folder. So that part only I'm connecting here. I'm just mounting it with my drive that is getting access from my actual Gmail account. So whenever I'll be running this code, it will even ask me for the permission to establish connection with the drive, because that is the safety feature we have on Google. So all of you will have to permit that access, then only it will be able to move forward. Once we have mounted our drive, then I'll be setting a path to store my dataset within the drive. So I'm writing here drive dataset path, and here I'll be making a fixed path in which I need my dataset to be saved. Drive, this thing we have already created, this portion. Now inside this, I'll be finding my drive, and then I'll be saving this COVID-19 image dataset. So this file path I'm giving. Next to this, I'll write here, in case if, because sometimes the paths do not exist. So in that case, I'll put some additional tests also. Maybe in case if drive path fails or if it doesn't work, we'll be copying it accordingly. So what I'll do here is, in case if file path that I'm providing does not exist, in that case, I'll take help from Shuttle library that I have already loaded, and I'll be copying the tree of my data. What is data tree here? The one that I have shown you. This is called data tree. These portions you can see, these are data tree. Means folder inside folder and folder, then inside that we have images. So that forms your data tree. So we are just copying the entire data tree in that case, and that will be from whatever fixed path it has taken, in case if it is not taking this path. In that case, whatever fixed path by default it is taking, from there we'll be moving everything to the path that is specified by us. So this portion I'm updating here. And once this is updated, after that we'll be able to print the data set if it is available in a specific repository. So that will be verified with the print command here. I'll be writing this portion, and here drive dataset underscore path. Okay, so let me just update this if it works fine. Otherwise, I'll be updating it further. Or I'll put one more fixed path over here for any kind of reference if required. The open path also I'll keep here. Contact.covid19 image dataset. One fixed path I'm keeping here that will be right here outside this entire repository. So if I run this portion, let us see if we are able to mount the drive first. It is downloading dataset. You can see the progress here. I'll be sharing this code once it is done. If it works fine, then I'll be sharing it. So you can see it is asking access to Google Drive. So I'll connect to Google Drive. It will look for the permissions. So the account permissions I'll be giving. All of you may have to do the same because this goes with the privacy policies of your drive. So once it is done, it is finding the original path. Then it will be setting up the drive path over here. And ultimately, your dataset will be available in that path. Depending upon how big is your dataset, you can see it will take some time. It says it is mounted here, and then dataset is available at this particular position. So if we want to find, you can see within Drive, I can find my drive. And then inside this, since I have many other data sets also, because I keep on working on different options, this is a data set that we have just now created. If I click on this, you can observe inside this, that entire tree is created now. So in the similar manner, your data set will be created that will be appearing on this side within your drive. Depending upon how much data you have in your drive, you will see a folder inside. So I'm sharing this entire data code with all of you. So those who are doing side by side, they can run this code and confirm in the chat box if you are able to visualize your data path somewhere here. Even if you are not able to find your data set, just confirm me that you are able to see this output. That data set is stored in your drive. That confirmation at least you should get. I'll wait for responses in the chat box. If anyone needs any help in between, they can also let me know if anyone is stuck anywhere. If anyone is doing, they can confirm me. Otherwise, I'll be proceeding further. What error you are getting, ma'am? Let me know. Let me know if there is an error. Before running this code, make sure you have logged in with your Gmail accounts. You need to put your code in the code cell that you can get from here. I suppose you have joined session right from the beginning. I explained this part right in the beginning. You need to insert your code in the code cell that contains a play button in front of it. There only you will be able to run it. After pasting your code, you need to hit the play button. Then only it will work. You can see this is also a code cell. If I need to insert more code cells, I can click on this code and one more code cell will be inserted. Inside this now, I can paste my code like this and then I can run this. So once you are ready with the data set, then you may need to import some libraries, some essential libraries that we need to establish things further. For instance, some basic libraries that I need include NumPy. That is the very first thing we need. NumPy helps us to do numerical manipulations on the data set. This looks strange. Okay. Let me know, are you using Google Colab for the first time? Ma'am, kindly confirm if you are using Google Colab for the first time. No? Kindly share your screen. Let me just see where you are stuck. Kindly share your screen. Yes, please. Are you able to share? Okay. Ma'am, you are on the Kaggle screen right now. I have asked you to open Google Colab. Kindly take me to that screen. We are working on Google Colab right now. As I told right in the beginning of the session, the data we have taken from the Kaggle and the codes we are executing on Google Colab platform. I have given you an idea about how we start with Google Colab right from the beginning. You just need to go to any of your browsers, search for Google Colab, enter into the platform, log in with your Gmail account, and then open new notebook in the drive. And there only you have to paste the code that I have shared. I suppose that is clear to everyone. Ma'am, kindly stop sharing. I hope this should be fine for you now. You are just on the wrong page. You just have to go to Google Colab page only. Thank you very much. So, okay, next we are importing some libraries here. The very first library I'm taking is NumPy. That is for any kind of numerical manipulations on the data set. Second library I'm taking is matplotlib.pyplot as PLT. If we need to plot anything, I'll be taking help from matplotlib for that purpose. And then because we'll be setting up deep learning based platform, so I need TensorFlow also for that. So I'm just importing TensorFlow as TF. And then from TensorFlow, I'll be importing Keras because I need to set up system layers, or we can say like the model layers we need to set up with the Keras framework. So I'll be loading Keras also here. Furthermore, from TensorFlow.keras, I need to import layers because the model requires several layers to be created, and those layers will be updating from here. After this, I'll be passing here the root address of my data file, and that I'll be taking right from here. This will be my root address now, or you can take the previous variable also as it is. But I'm just making it specific that this is my dataset root right now. And from here only, I'll be taking all my data files. Then I'll be declaring few essential variables. First is image size that I'll be taking 224 cross 224 because this is the standard size of input image required by EfficientNet model because we are using a pre-trained model. So based on that only, we need to fix up image size. Depending upon which pre-trained model you are using, accordingly, you may have to choose your image size in that case. Next thing I'll be using is batch size. And this is 16, for example. This is a good batch size, we can say, for running a very simple model. Otherwise, you can later on try different batch sizes also, like maybe 32, 64, or larger as well. Then a seed of 42 I'm putting here. This is just a random number. You can put any value instead of this. This is just to ensure reproducibility of all the executions that you are doing here so that it runs with same number of random variables every time instead of changing those base variables. So that is why seeds always we put initially while setting up our system parameters. Then epochs I'll be passing is equal to 10, for example. I'll not run a very in-depth model. Rather, I'll be running a very basic model with 10 iterations only. So these are some essential variables and libraries that I need to set up in the beginning. And I can see the green tick right here. Whenever I run a code, it is important to ensure that we are getting a green tick in front of it. That only will assure that we are able to run it without any error. So once we are ready with the libraries, the next part is we'll be setting the train and test paths. Set train and test paths now. If you remember, when I have shown you the tree structure of this data set, you have seen that there are train and test folders within COVID-19 dataset. So we need to reach to those specific folders to assure proper training and testing file path. And how we can do that, I'll be updating that path information here. I'll write here first train path, and second I'll be passing here is test path. Both of these paths I'll be updating one by one. I'll be linking it with the help of operating system path, and I'll be joining it first with dataset root. If you remember, this is your dataset root because this contains our main information. And then inside this, the first main folder we have is COVID-19 dataset. That was the first main folder we have. And inside that, we'll be linking to the train folder in this case. And then second case, same sequence I'll take, but this time I'll link it to the test folder. Remaining all things will stay the same. So in this way, the train and test path I'll be able to link up to, and that is directly available here inside this path that we have recently observed here. You can observe COVID-19 image dataset, then COVID-19 dataset inside this train and test path. So this path basically we are defining here, and we are joining it with the help of operating system. So I'll be running this. I got a green tick mark, and I'll be sharing this one. The seed value we insert to ensure reproducibility of all the results that we are getting here. For instance, when you are running certain models in deep learning or in machine learning, etc., there are some initial weights that are generated every time. So when you want to fix those weights to a specific value, even if you run multiple times, then we give a specific seed value initially. When we fix seed to certain random value, this is a random value. It is not like 42 has a specific meaning here. You can put any number here, but this will just assure that every time it generates the same set of random variables to run on your file. Similarly, epochs, these are the number of iterations that we'll use to run our model during the training process. So 10 iterations basically we will apply to our model during the training process further. So these paths I have updated, and I suppose I have shared. Yes, I have shared them here also. Now the next step we will do is we'll be creating directories, create train and validation directories, or we will create one test directory also. So all three directories will be creating now. The path we have attached, but as you know that currently we have only train and test repositories. But for running a good quality model, especially when we are working on deep learning, we need validation dataset also. There are generally 3 sections of data. Training dataset we use to train our initial model, to make it aware about what kind of application it has to run upon. Validation dataset is a part of training dataset. It is basically splitted from the training dataset itself. So the similar kind of pattern it follows as that of your training dataset. But it is used to evaluate performance of your model side by side during the training phase. So some set of training batches will be passed into the system. It will be running on that. It will see how well it is learning. And in the validation set, it will be testing whether it is able to remember those learnings or not. And then ultimately we have test dataset. Test dataset is a completely unseen dataset because it is already in a separate folder also, as you can see from here. So that is like a whole new set of data that we put into the model to see if it has been trained well and it is ready to be deployed into some real-time scenarios now. Sometimes test dataset can be something like you take real images of chest x-rays from patients, and then you deploy them into your model, and then you try to see whether it is working fine as expected or not. So currently we are having all types of dataset with us. Train and test we have, and validation dataset I'll be creating here. I'll be just splitting some portion from the training dataset to create the validation one. And how I'll do that is, first of all, train DS I'm creating, train directory basically I'm creating. The process is very simple. I'll go to TF Keras, that is your TensorFlow Keras, and then we'll go to the pre-processing module. Here I'll pass image dataset from directory. This function is readily available. Now inside this, what I'll do is, first of all, I'll mention train path, because we are creating training repository. So train path we need for this. Second thing, the labels I'll pass. And for this, I'll write here inferred. Inferred labels means when we want to assign labels automatically as per the folders available in dataset. And if you know, the folders available in dataset are COVID, normal, and viral pneumonia. So these three will be considered as labels, and they will be automatically extracted as per the names of the folders. So that is why we write here inferred. Then next thing I'll write here, label mode is equal to categorical. And then validation split I'm passing here is 0.2. So 0.2 here means I'll be using from the training repository, I'll be using 80% data for the training and 20% for the validation. So that is why validation split is equal to 0.2 we are mentioning here. Then subset is equal to training. This repository, I'm giving it a name train DS, you can observe. So this will be containing training subset. That is the 80% portion. So that only it will be updating here. And then seed, either I can pass a number here, or because seed value I have already declared in the beginning, so I'll be using that here. If you remember, this capital seed we have already declared, so that only I'm passing here. Then image size, another parameter, because when we are putting these into specific repositories, we need to assure that they are saved in specific required size. And that size also we have mentioned here in the beginning. So I'll be using the same variable here, image size. And then batch size is the next thing I'll be passing here. And I hope batch size also we have mentioned here as 16. So that also I'm updating. So in this way, all the relevant parameters to create training repository I have passed. Training path, labels, mode of labels, categorical we have mentioned because these are categorical variables. You can see these are alphabetical type variables. We call them categorical in nature. If you have variables like 0, 1, 2, 3 or 0, 1, they are binary variables, or you have number type variables. So it depends on how your distribution is going on. Currently, we have these COVID, normal, and viral pneumonia. These are categorical kind of distributions. So the label mode we have mentioned is categorical here. Validation split I explained, and all these things we have already declared. The same we are using here. In the similar manner, now I'll be declaring the next portions, that is validation DS first of all, that is validation directory. And for that, I'll be taking the same thing that I have mentioned here. Just slightly, I'll update things inside. First thing, train path I'll keep as it is. Labels will be also as it is. Label mode as it is. Validation split as it is. Just the subset I'll change to validation, because this is validation directory. So validation subset I'll be using inside this. So only 20% data will be taken now. The remaining 20% basically, because we are already splitting that into 80-20. And now the third one we need is test directory. So this test directory also will be creating with few essential parameters only. So this initial function will stay as it is. Here we will mention test path this time. Label inferred is fine. Label mode categorical is fine. And these two things will not be required this time, because test dataset we are using as it is. We are not creating any kind of split or subset from there. So these are the essential details required for the test dataset repository. So now we have created 3 sections. And from here, I can even extract class names, because that will be required later on while setting up the model. So those class names, I'm just extracting here from any one of the repositories, like maybe train DS, because similar class names we'll have in all categories. And if we want to see those class names also, we can visualize them here side by side. Like maybe I'll write here classes, and I'll pass here class names inside. So I'll first run this. Let us see what we get. I have a typo. Let me just check. The repository, it is not able to find. Let me just correct. train path I have updated here. From directory inferred. Training batch I have updated. This is test path. Let me just check why my path variable is not working right now. Okay, I can see that I have a typo here. You can observe if I check this COVID-19 dash dataset here, by mistake I wrote underscore. This is the problem. All of you need to correct this. Everyone, please check. We have dash here, not underscore. If I rerun this, after making correction, I have to rerun this portion and then I'll run this again. And this should work fine. I got the green tick, and you can see these are the files that it could extract from different sections. So I'm sharing both of them again. Those who are doing it side by side, please make sure you do correction in the previous one also, where we are updating file paths. And then you should be getting different portions of your data. So now we have created all essential libraries from our, or directories from our dataset. Let me know if it is clear up to this. Just let me know quickly in the chat box if all the points are clear up to this. Accordingly, I'll proceed further. Thank you very much for the update. I hope others are also able to do. Now, the next thing I'll do here is I'll perform data augmentation, for instance. Data augmentation, generally, we prefer to do whenever we are working on image files, especially when we have small size data. Because in my case also have taken a very minimal range of data here. So augmentation basically help you to create multiple replicas of available images. There are plenty of augmentation techniques that you can use, like zooming technique, rotation technique, flipping technique, and many of them are available. Fading, noise insertion, etc. Plenty of things are possible. But depending upon what kind of data set you are dealing with, some of the augmentation techniques may be useful, some may not be useful. So that completely depends on your data. For instance, if sometime you are working on maybe alphabetical sequences, alphabetical data you have, like ABCD, just recognizing some alphabets only. So a vertical flip on alphabet or a horizontal flip on alphabet will not be useful, because that will not represent actual version of your alphabet. That will be just creating a poor version of your data. However, if I'm talking about chest x-rays, then maybe a horizontal flip will not make a big difference. However, vertical flip will make a big difference. So horizontal flip may be a good thing, a reliable thing in that case. Similarly, in case of rotation, in some data sets, a little bit of rotation is fine. However, in some other data sets, maybe rotation will change entire meaning of your data set. So completely depends on what the type of data set you are dealing with. You choose augmentation techniques accordingly. Sometimes beginners have to do hidden trials with multiple augmentation techniques. Currently, depending upon the available time, I'll be using just a very simple technique for augmentation here, just to give you an idea about it. So for instance, I'll put here data augmentation. And for this, I'll take help from Keras. I'll go to the sequential model inside. And then I'll be passing here layers dot random flip. That is one type of augmentation I'll be applying. And that is horizontal flip only I'm doing. I'm not doing vertical flip. Just few options only I'll do here. Later on, you can do other options also. There are plenty of augmentation options that you will find in Keras repositories. Random rotation also I'm doing. and I'll be doing a very small rotation of like 0.1, very basic rotation I'm applying. And then one more augmentation layer I'll be updating here, layers dot random zoom, for example, I'll do. And inside this, again, a 0.1 value I'm passing. So random zoom 0.1. If it is a positive value, that is zoom out. If it is a negative value, that is zooming in. So currently I'm doing zoom out because I'm putting a positive value here, positive 0.1. If you put minus 0.1, that will be zoom in. So accordingly, you can put your values. I'm just testing it with 3 changes only. After doing data augmentation, here I'm passing one more parameter, that is auto tune I'm declaring here. And with this auto tune, I'll pass here data dot auto tune. What it will do basically, although this is an optional technique that we pass, it is not always required, but this auto tune basically allow TensorFlow to automatically determine the essential number of elements that should be prefetched into the memory while running your image data set into the model, so that whenever the GPU is processing your data and CPU is getting the next batch of data, there is a proper flow of information between both sides, and nothing is required on the like we need not to wait so long to load that data set. For that purpose, we pass auto tune here. And this I'll be doing here in multiple sections. For example, training directory, I'll be first connecting here, train DS. And this I'll map with, I'll be basically passing my this data augmentation into this. Just all the versions of data that I have created with augmentation, like the flipped version of data, rotated version of images, zoomed version of images that I have created, all of them that then I'll be updating into my training repository as well as into validation repository. We will not apply augmentation on the test repository, that will use in the clean version only, that is its original version. Only training and validation data will be doing augmentation. That will be, we are just slightly enhancing this data set with some new versions of images. So here I'll be passing lambda variable, that is your anonymous function in Python. That is just a very short range function we can create. Just create it, execute it, and then nothing to save in the memories. In that case, we use these simple lambda functions. So efficient net dot preprocess input X with reference to Y. So both elements I'm passing. X and Y basically represent two things. X is your input sequence, Y is your output sequence in your library. So Y basically represents your labels. X represents your input images sequence. And this I'll be saving with train DS is equal to train underscore DS. And prefetch routine with auto-tune, so that all the time the memory contains the recent set of batches instead of being in the wait state for a longer time. So this is for the training data set, and now the same thing I'll be doing for the testing data set. Here also I'll pass map function, then lambda x comma y portions we are creating. Inside this tf.keras.application, this is applications repository, and inside this efficient net dot preprocess input, exactly same that I have done above. Just the two portions of data we are creating in the similar manner, that is for your labels and input sequences. And then for the validation directory also, we will pass the auto tune, so that this also stays ready all the time whenever the fetching sequence is working on your data variables. So these are some essential portions we have passed for preparing the next batches of data set, so that parallel calls keep on running on all batches of your data, and it keeps on doing the augmentation wherever required. It will be updated in every step accordingly. So I'm just updating this portion and I'll be running this here. Let me check. We have some typo somewhere. This one. We have prefetch. I'll be running this and this looks fine. I got the green tick for this also. I'll be sharing this now. All of you can run this. So with augmentation, now we are ready with the new set of updated images that are flipped, that are rotated, that are zoomed slightly. So we have just populated our data set with some new versions of the images, so that more robust prediction we can do with our pre-trained model. And in the next step, I'll be updating here, use efficient net B0 as pre-trained model for prediction. I told you right in the beginning that I'll be using efficient net B0 as my pre-trained model. So whenever you are working on pre-trained models, there are so many ways to use them. Sometimes we deploy those models directly as it is because they are already trained on a very extensive data set. You can sometimes apply them as it is to make predictions on any new data set. This, do we have any query, please?
நான் வரும்போது தான் கொஞ்சம் சோறு தின்ட்டு வந்தோடனே
If not, I request you all to mute yourself.
காட்டுல மாடு சோறு மட்டும் சோறு தின்னுட்டு இருந்தேன்.
Thank you very much. So I was on, yes, efficient net B0. So for the pre-trained models, we generally sometimes have to modify their initial input layers or the classification layers. Sometimes we have to modify depending upon the new set of data that we are giving. So the base model will keep as it is. That will be your efficient net B0. Just few elements out of this we will freeze so that we can make them ready to handle this new set of data. That is our disease specific data. Otherwise, image net data set on which this model is by default trained, that contains a variety of images. That is like a very large range of images it contains. Like 5 lakh around something images it contains for the training and the testing purpose initially. But currently we need to train it on our kind of images that are disease specific images. So for that, little bit of adjustments on the model I'll do. First of all, the base model I'm calling, and I'm using Keras applications efficient net. You can see there are so many versions of efficient net. I'm currently using the basic version B0. I'm using for this. And inside this, I'll be passing some relevant parameters. First thing, include top. I'll be writing false. I'll be loading the network that doesn't include classification layers on the top, because those classification layers we will be adding as per our requirement based on the data that we are providing. So by default, top layers I'm not adding from the pre-trained model. Then weights we take as it is because it is trained on ImageNet dataset. So those only weights we are taking because the main time goes in weight training, and that time basically we are trying to save while working on pre-trained model. That is basically to save our time. And similarly, the input shape I'm passing here, and that shape I'll be taking from the size that I have initially defined. So 0, that is your first section, and then 1. We have defined 224 cross 224. That only basically we are giving here. First 224 defined with 0, second 224 with 1, and then 3 channels because RGB colors basically that are by default processed with image, this efficient net B0 model. So 3 channel description we provide with this RGB layer basically. Then pooling layer we are passing here. By default, average pooling layer it accepts. So that only we are passing. So this is the base model we are setting. Now, inside this base model, trainable I'm making false. This is very necessary. We are just freezing the training process because we don't want to train it from the scratch. Rather, we want to use the initial weights from ImageNet training as it is, and then only few new layers for the classification purpose will be adding as per the requirement of our dataset. So we are not making it trainable right now. Rather, some layers only after this will be updating. That will save our time. Instead of creating a new model from the scratch, we'll be using the existing information from the already trained model. And inside this now, I'll define few things. First is inputs, because based on our dataset, we need to set the input layer. So input I'm passing here with the shape of image size that we have already defined, 0, 1, 3. Okay, there I'm making a typo. Let me just correct this one. This will be within square brackets because these are the index values. Index values are always in the square bracket. So these two elements regarding shape I have updated. Then X I'm updating here. The augmentation layer I'm passing now. Augmentation we have already created. So that layer only I'm passing, and I'm attaching it after my input layer. You can observe this thing decides where you are attaching your new layer. So first layer I'm creating is input layer. After input layer, the next layer I'm passing is augmentation layer, and that augmentation layer we have created here. I'm using this layer only. These 3 layers in augmentation layer we have already added. So this is the sequential model with all these essential layers we are updating. Then next thing, tf.keras.applications.efficient.net.preprocess input. So essential pre-processing, whatever is required by the system, that only will be updated here. After this, we are passing the base model that we have already created. And inside this base model, the training we are again mentioning here to be false, because we don't want to train the base model that I have made false here. And after this, the layers dot dropout I'm passing. The dropout ratio can be anything. In my case, I'm passing a 30% dropout. So randomly, it will turn off 30% connections anywhere during the training process. And this dropout basically helps you to create a robust model that can provide you more reliable or accurate outcomes, even if some layers are turned off, some layer connections are turned off in between. But that is the purpose of dropout layer basically. Then the output layer we need, and we add a dense layer on the output layer of any of your deep learning model generally. So length for dense layer will be as per your class names, because there are 3 classes. So this will be automatically with level 3. If there are more classes, accordingly that level will be changed. So currently we are creating a 3-class model. And on the final layer, the function or the activation function we are passing is softmax. This is a preferred activation function for the final layer of a model. And we are attaching this output layer to the previous X layer. Means after dropout, we are passing this dense layer, and the name to this I'm giving is output layer. And ultimately, the model I'm setting up here, keras.model.inputs and outputs inside this I'm passing. So everything that I have defined here, like the base model I have given, the settings of base model I have done, then input layers along with its multiple sub layers I have created, then output layer I have created, and then finally I have set up the model here. And after fixing up this model, the next thing is we need to compile this model. So model.compile I'm writing here, and inside this I'll pass optimizer is equal to keras dot. There are plenty of optimizers in Keras. Many of you might have used these optimizers. If anyone is new, there are like 7-6 different optimizers that you will find. Like ADAM optimizer is there, ADAM is there, RMS prop is there, and gradient descent is there. Many of the options you will find. By default, generally, majority of models we use are with ADAM optimizer. But you can do hit and trials by changing these optimizers also. You can change this name maybe to SGD, maybe to ADAGRAD or any other optimizer later on, just to see how it impacts overall performance of your model. So these kind of things you generally do while improving accuracy of your model also later on. If maybe your DAM is not working fine, you can try some other optimizer in that case. Then learning rate I'm passing is just a random value, e raised to the power -3 I'm passing. Maybe later on you can try some other values also. So currently just one random value I'm trying here. And then the loss parameters I'll be passing, and that will be categorical cross entropy, because currently I'm working on a multi-class problem. So I'm using categorical cross entropy, categorical multi-class problem, because I'm using, in case if you are working on binary problems like 0, 1, etc., in that case you can use binary cross entropy also. So there are different loss functions that you can utilize as per the requirement. And matrices for model evaluation I'll be using is accuracy. So that also I have passed here. And then the model summary I'm utilizing here. And let me just run this. If there is no typo, this should build a basic model summary. Let me just check this one. Yes, and this dot is not required. So this is setting up your model, you can observe. And these are the model layers right now, the parameters and the shapes, etc. Like layer by layer, this thing we have already created, if you remember. So all those things now it has created, and how many parameters are working inside, because we are using pre-trained models. So from there also it is getting some parameters. Accordingly, the parameter sequences it has updated for the base model. So I have shared this with all of you, and let me know quickly if this is clear up to the level. Then I'll start with the model training in the next step. Just quickly let me know in the chat box if the things are clear up to this. Okay, thank you very much. So the next step I'm updating here is to train our model. So I'll be running this here, and the history I'll be storing for model fitting sequence, and the train DS I'm passing. Then next thing I have is validation data. That will be your validation DS. Just some essential parameters only I'm passing. And then epochs, as we know, we have set up 10 epochs in the beginning. So these are some essential parameters that we need to pass to fit our model. Fitting sequence requires training repository, validation repository, and number of epochs on which you want to fit your model or train your model. So I'll just run this, and okay, I have a typo here. I need a comma at this point. Now you can observe the training process. I think it started, but maybe some typo can be there. Let me check. Input shape looks fine. 0, 1, 3 we have passed, and here also looks fine. Yeah, training is going on, so this is fine. It is taking parameters here one by one. I'll be sharing this with all of you so that you can also start with the model training. So this will take a little bit of time to set up your model. The training epochs will run because there are 10 different epochs on which it will be running. But in the meanwhile, we'll be writing our next set of code. It will keep on working for some time. We will let it here, and we can start writing further in the meanwhile. That will be to save and evaluate this model. So the next task we'll have to do. So I can save this model right here, model.save. And I'll write here COVID diagnosis using efficient net. So I'll give it a nickname here, efficient net v0, and .h5 version I'll use for the model saving. There are different versions by using which you can save your model. .h5 version is generally the most commonly used one. .keras version is also used sometime, and there are few other versions also to save your model. But this one works fine with majority of cases, so I'm using it here, .h5. Loss and accuracy parameters also I'm saving from the model. So model.evaluate, I'll write here. Test_ds, I'll update here. Then we will print the model accuracies. So mainly validation accuracy, we'll try to see that what we get as validation accuracy from this model. So I'll write here accuracy multiplied by 100 to F. Up to 2 decimal places, basically, I need to get the accuracy. So it will give you accuracies first in this format, then I'm multiplying it with 100. And in terms of percentage, I'm trying to see up to 2 decimal places. So that format only I have updated here. So this I'll be closing. This one is not required. Here I'll be using this. So this will be to save as well as to print outcome of my model. And you can observe this is also done almost now. It is 13 by 13, 6 by 10. Okay, epoch, six epoch is running right now. So after this, we will run this portion, and then we will be working on the testing phase. So I'll write here test model on random data. This portion I'll be sharing later on. Once the training phase is done, I'll be testing this portion, and if it works fine, then I'll be sharing it. In the meanwhile, I'm writing the final set of code that is to test your model on the random data. And for that, what I'll do here is for image and labels in test repository, we will take the first batch. It will take the entire first batch. So in our case, the batch size is 16. So it will take 16 images from the first batch directly. Then we will make predictions on those images. So I'll write here model.predict, and those images will be passing inside. And after this, I'll run a for loop up to the range of 6, for example. You can do for the higher range also. I'm just plotting 6 only right now. So from those 16 images on which it has done predictions, I'll be taking just first 6 only for a quick subplotting here. I'll write here plt.subplot 2, 3, I plus 1. So this is what subplot sequence 2 cross 3, that is your positions. So number of rows, number of columns, and position. 3 things we are passing here. So 2 number of rows, 3 columns, and this will be the position one by one that will be set it up for the plotting sequence. Then plt.imshow, and inside this I'll be passing the images one by one, because here we are running a for loop over 6 images. So first I dot numpy will be converting it into uint 8, because that is the by default version available for the plotting purpose. This will ensure that your numbers are again converted into 0 to 255 range, which is the best possible visualization range required for images in your Python repositories, or when we are using IMShow basically. So that conversion into uint we are doing for better plotting. And then after this, true label I'm inserting here, class underscore names, np.argmax. Inside this, I'll pass the labels that are predicted by the system. So that I'll be passing inside here. These are the true labels. We are getting it from the actual labels basically. Then second case we have is with predicted labels. So here also the class names we are passing np.rmax, generally because you are getting the range of probabilities in the outcome, and now we are converting them into the best possible outcome that we can predict out of those probabilities that we are getting as an output of your efficient net model. So those final true labels and predicted labels will be getting from the sequence here, and we'll be updating it in the final sequence. We should get a green color if true label is equal to predicted label. If both are same, then it should be printed with green. Otherwise, it should be printed as red. The label should be printed as red so that we can identify it quickly that it is a wrong prediction or right prediction, because that completely depends on how accurately your model is working. And if I scroll up, okay, these 10 epochs are done. And if I run this portion, we can visualize here how well your model predictions are working. So it will just take some time to update your validation sequences. This looks working fine. So all of you can also do it side by side. So this is your validation accuracy right now. So this is 81.82%. Not like a very good accuracy, but up to some level we are getting a good accuracy, like, because this is above 80% at least. So now based on this, what prediction it will make on test data, that we'll be seeing further. So for this, what we'll be doing is plt.title. I'm making here inside this I'll pass true. That will be with respect to true label made by the system. And in the next line, I'll write the predicted sequences. And inside this, I'll write predicted label by the system. And then the color I'll be updating equal to color. So this title will be automatically updated into your final plots. Then PLT X's I'll keep off because X's information is not required in this case. And show I'll turn on. So these are few just for the plotting purpose we are updating this. What we are doing, let me explain you again. First, we are taking first batch of data from your test repository that will contain basically 16 images because we have a batch size of 16. Then we are making prediction from the trained model on those 16 images or that first batch. After that, I'm going ahead with the plotting sequence. And for that, I'm running a for loop over a range of 6. So up to 0 to 5 index, it will be running basically. And then we are creating a subplot with 2 rows, 3 columns, and position we are updating every time based on this I sequence in the for loop. Then we are showing the images, whatever images we are passing during this I sequence or I iteration. Those images one by one we are updating, and we are showing them as uint8, that is basically your scale value between 0 to 255 to display any kind of images. And then true labels we are getting, that is the expected label, and then this is the predicted label from the system. Both of them we are updating here. And then we are just ensuring if both labels are same, they should be updated in green color. If both labels are different, they should be updated in red color. And accordingly, the titles we are updating for every subplot, and the axis information we are turning off, and we are running the plot show curve here. Let me just check. We have some typo in between. Images, this one. Okay, here I need to write images. So I'm just running this now, and let us see how it works. Okay, just one it could give. Breads. Okay, this is breads. So I need to update this also with breads. Now this is fine. You can observe wherever we are using right prediction, it is coming in green color. Just this one is wrong. It was expected to be normal, but it predicted as viral pneumonia. So these are the predictions that this model is able to make, and we are displaying it with the X-ray images. So whatever we are getting from that test batch, based on that only, it is updating those outcomes. So all of you can run this one as well. I'm sharing this test image code here in the chat box. You can run this and check if you are getting these kind of outcomes and if you are able to observe how your model is making prediction on your test data set. We are comparing it directly with the images also side by side for the normal as well as COVID affected or pneumonia affected X-ray images. So this is just a complete overview I have basically given you right from the scratch. We have obtained a specific image, then we have tried extracting it one by one. If we go with the entire flow that we have taken, observe it, those who might have missed any point in between. See, in the very first step, we have taken it from the Kaggle directly, and we just tried to load data set from this Kaggle repository to our drive directly. And then in the drive, it was stored at this particular path. And from this path, then further, we decided the dataset route. We loaded some essential libraries, and then we updated some essential variables that are required time and again throughout the coding process. So that is why we have declared write them in the beginning so that we can use them time and again. Then we have set up training and testing paths so that we can extract files from these repositories directly, because we already know that path for your data is mentioned into these repositories. We can see train and test repositories. These directories are already within your folder. So we need to access them accordingly. So train and test repositories we have created. Then from the testing, I split it up one more directory, that is validation directory, because whenever we are training a deep learning model, we need validation data set also, and that is always extracted from training itself. So 80% of data from training repository is used for the training itself, and remaining 20% I'm putting into the validation data set, and the testing one I'm keeping as it is. So all these sections were created, and we can see these portions of data being created after running these separate directory paths. Then I have performed data augmentation, where I just created like some new versions of the existing images. Some of the images are slightly flipped horizontally. Sometimes they are just rotated by a small angle. They are also zoomed slightly by 0.01. That is your zoom out sequence. So accordingly, just three different types of augmentation techniques I have applied to populate my data with few different versions of the existing images. Then auto-tune also I have applied so that every time my memory sequencing goes fine and the model during the training process doesn't have to wait for the new batches of data. Rather, they stay always in the memory, and they are fetched immediately whenever called by the model. So that is why the auto-tune process we have set it up here. Then I have called my efficient net model. The base model I have kept as it is with image net weights. That is your base version of data on which efficient net B0 is trained. So those weights I have kept as it is. And I have not retrained this model. Rather, I'm using the pre-trained version of it. And after that, I have set it up some new layers into this model that are specific to the new data that I'm applying, so that this data set is processed well by the pre-trained model, and it can give us desired outcomes. And once we have added all the essential layers into the model, then we are compiling this model, and this is the structure of the model that we have created. Along with some custom layers, we have added the base model efficient net B0 here, and the parameters of the model are updated accordingly. Then we are training our model only up to 10 epochs. You can later on change it up to 100 epochs, etc. Accordingly, some time limit will be changing for the training process. Since we had limited time here, so I have used only 10 epochs right now. After training our data set or our model for a limited set of epochs, we are further evaluating it, and also we are saving this model. Like you can observe it here in your this section. I'm just saving this model right here. Maybe if you want to use it later on, you can download it from here and you can deploy it anywhere in the APIs. So we have also tested how well it is working on the validation data set. And then I have finally tested it on some random images from my test repository. And this is the outcome we are getting here. So I have just summarized entire session for all of you. And I suppose I have given you some relevant information on the topic here. If we have any kind of queries or any discussions left on the topic, please let me know. You can post in the chat box maybe if you have any queries, any feedbacks.
Good evening, ma'am.
Yes, please.
Ma'am, I know why you're using only KDAS.
Ma'am, that is just one option we are using. That is one of the most simplified open source deep learning API that people generally use for training and building neural network. It is one of the most powerful API frameworks generally we have. Other than this, also you can try some different frameworks.
Okay. And label mode, you have given categorical, ma'am. What is the purpose?
Okay, for that I explained earlier also, like when we are having data set into your different repositories that are alphabetical sequences, like I have shown you COVID, normal and viral pneumonia. So that are categorical values. If you have simple binary values like 0, 1 are your target values, they are represented as binary values. But in our case, we have alphabetical sequences as our target variables, COVID, normal, and viral pneumonia. So that represent categorical value. That is just a type of data, basically. Categorical or numerical, these are some different types of data we have generally.
Okay, thank you, ma'am. And what do you suggest, ma'am, if someone wants to implement projects on deep learning? So shall we start with KDAS only?
Yes, Keras is one option for the beginners you can start with. However, later on you can go ahead with PyTorch also. These are some commonly used option for deep learning models.
And this
TensorFlow
project
and Keras generally work side by side because they have many common repository to share with each other. However, PyTorch is also a complete that can work maybe like a complete Pythonic interface for you to support several distributed training processes also.
Okay, and you run on the CPU only, no, ma'am? Just no.
Yes, currently I'm using the free version of Colab, so they generally dedicate you CPUs only. GPUs they dedicate very rarely for the free versions.
Okay, thank you so much. Thank you. It's a great informative session. Thank you.
Thank you very much, ma'am. If you want to change weights of your model, then you may have to go with some fine-tuning processes, or sometime you may need to replace the final layers, or maybe you need to train some new layers on your model. So weight changing process for your pre-trained model is like a little complicated. And sometimes you even end up creating a very overfitting model because if your weights are not fitting well. But still, this is a part of fine-tuning. If you spend some time on fine-tuning, if you adjust hyperparameters of your model, you are able to get some good set of weights also. That is possible. There are multiple ways you can do this. Any other queries or feedbacks, please let me know.
So if participants have any questions, they can ask our expert, madam.
Code files I'll be sharing with the coordinators also later on. So all of you will be getting them. There will be no problem in that. See, setting up a code for changing weights is not a simple task. As I told you that this is a fine-tuning process. It requires sometimes several weeks or several months to set up your fine-tuning itself. But the process is something like the fine-tuning includes updating several things. Like sometimes you can update optimizers, maybe from ADAM you can change to SGD or maybe ADAGRAD, etc. On the learning rate side, maybe you can change from currently we have used 1 e raised to the power minus 3. Maybe you can change from e raised to the power minus 4. These are some common hyperparameter changes that we can focus on. So other than this, you may have to change your training iterations also. Currently, we are using only 10 iterations. You can update it from there, from that further also. These are just some basic hyperparameter changes. Other than this, you can go with some rigorous hyperparameter changes also. That is based on the freeze layer that I have used initially. You can unfreeze them. Instead of using pre-trained model as it is, you can make those layers trainable. If you remember, I have at one place that trainable equal to false I have done. In that case, you may have to do true in that case. And that will recompile your model by changing all the attributes inside, and it will take like several hours to recompile everything from your model. And then only you will be getting the new weights from it. So this is a long-term process. You cannot do it instantly. And also, whenever you are doing all these things, there is no guarantee that in one go you will get a better outcome from your model. It is like a hit and trial and error process. It goes. You make one change, then you see impact on your model outcome. You make other change, and you see impact of your. Sometime it will be a positive change, sometime it will be a negative change, and you may have to adjust all the hyperparameters accordingly. If you want to run it on local machine, then Jupyter Notebook is one good option that you should try. Other IDEs are not so much suitable. Jupyter Notebook is one good option that you should try. But make sure you have high-end GPU if you are working on deep learning. Otherwise, it will be very difficult to run it on your local servers, local machines. The GPUs are must to run good quality deep learning models. So maybe some high-end computers you may have, or maybe in your labs, if you have good high-end GPUs with your systems, there also you can run it easily. Yes, Jupyter Notebook you can use for research. That is an authentic solution you can use. So thank you very much, everyone. Thank you for your valuable feedbacks as well.
Thank you, madam.
Thank you, sir.
For your excellent session. Thank you.
Thank you very much, sir. Thank you.
So dear participants, so today we conclude the session here, and tomorrow is our last day of our FDP, and tomorrow the session time is from 2 p.m. From 2 p.m. we start the session, and 2 p.m. our expert speaker is Bipin Gupta sir. Then 3:30 p.m. again Dr. Jagriti Shaini madam. Then the last session start from 5 p.m. Taken by the Shushoban Chandra sir. And finally, after that, from 6:30 to 7, we take the online feedback. And at 7 p.m., we start our quiz, and followed by the valedictory session. Okay, thank you. Thank you all.